Welcome to APA's weekly webinar series. My name is Billy Zydick, Manager, Special Projects for APA. Just a couple of housekeeping items before we get started. The webinar recording will be posted to the APA webpage later this afternoon. You'll receive a follow-up email in the next couple of days with a link to the webpage where all webinar recordings are housed, as well as a link to our upcoming webinars. We have webinars planned out through the end of 2021, and many are open for registration. Professional continuing education and AIA-CLU credits are being offered for today's program. If you are an AIA professional requiring a certificate, please send an email to me at Billie, B-I-L-L-I-E, @apa.org, along with your AIA membership number if you have not done so in the past. All attendees are in listen-only mode. Please type your questions in the chat box and they will be answered in the order they are received. If we run out of time and we still have questions, responses will be sent directly to the person asking the question by one of our presenters. At this time, it's my pleasure to turn this over to Monica Kyle, who will introduce our presenters. Monica, take it away.
Thank you, Billy, and thank you everyone for being with us today. The topic for this webinar is the efficiency opportunities of a comprehensive water management program with a focus on chiller efficiency. In a couple minutes, I'm going to introduce our presenters, Mike Doyle and Larry Siegel. Before that, I'd like to cover Phigenics bias disclosure. Next slide, please. Phigenics provides independent expert guidance for the development. Oh, excuse me for 1 minute. Phigenics provides independent expert guidance for the development and implementation of water management programs to prevent building-associated injury and disease and to improve operational efficiency for facilities. We provide real-time monitoring solutions, cloud-based data management, and environmental testing for all waterborne pathogens and analytical services for water chemistry. Phigenics does not sell water treatment chemicals or disinfection products, nor do we have commercial affiliation or funding from suppliers or manufacturers of such products. Next slide, please. Just a very quick introduction to Phigenics. Our core purpose is to help facility managers optimize the total cost of their water systems by improving safety and efficiency. Next slide, please. I'm also going to review our learning objectives for today. So following this webinar, attendees will be able to explain how a comprehensive water management program can be used to capture efficiency gains in a building water system, describe how chiller efficiency is an important and significant part of a water management program, identify the challenges that arise in maintaining chiller efficiency and the short and long-term financial impact of not addressing them in a timely manner, demonstrate how to easily monitor, trend, and identify challenges by analyzing readily available data that you're probably already capturing, and finally, discuss manual and automated methods for analyzing the data, calculating ROI, and easily managing your chiller efficiency using a minimal amount of time and resources. As Billy had already mentioned, we will have time for questions, so please start sending them in now using the chat function. Next slide, please. Our first speaker today is going to be Mike Doyle. And a couple facts about Mike. Mike has over 35 years of construction, facilities, and utilities management experience. He has a bachelor's in mechanical engineering from the Naval Academy and a master's in construction management from Penn State. He spent 27 years in the Navy before retiring as a captain. In 2009, he joined Phigenics as the VP of Operations. His responsibilities include engineering and technical oversight for the development and implementation of water management programs. Next slide, please. And our second speaker for today is Larry Siegel. Larry has over 50 years of experience in the heavy industrial and commercial air conditioning service business. He has a bachelor's in mechanical engineering from the University of Dayton, and he received a commission in the Army Corps of Engineers and served as an engineer platoon leader in Vietnam. Another really interesting piece of history is that he led the way in helping solve the ozone depletion CFC issue by performing the world's first commercial conversion of 3 large centrifugal chillers, that's a mouthful, from CFCs to HCFC refrigerant. So that's a really interesting fact about Larry. With that, I am happy to turn this over to Mike to take us through the content for today's webinar.
Thank you, Monica, and good day to everyone. I think it's morning some places and afternoon in others. I'm glad you could join us today. I hope to cover the learning objectives Monica described and more in the next 30 to 35 minutes with plenty of time for questions. So let's get right to it. A comprehensive water management program is a documented, ongoing program that, when implemented properly, optimizes the total cost of building water systems by improving safety, efficiency, and asset preservation. It includes all of the different potable and non-potable uses of water in a building. We start with ASHRAE Standard 188, which is a water safety standard, and then we adapted the hazard analysis process within the ASHRAE standard to help identify efficiency opportunities. Therefore, a comprehensive water management program covers the safety and efficiency of all building water systems: faucets, showers, ice machines, fountains, boilers, cooling towers, irrigation systems, and in healthcare, we include specialized systems like sterile processing and dialysis. And when in a campus environment, we include the heating and cooling plants, as well as the potable and utility water distribution systems. So the reason a comprehensive water management program includes efficiency as well as safety is explained by these 4 interlocking puzzle pieces. Your efforts to improve water efficiency will affect safety and vice versa, sometimes negatively if you are not careful. A comprehensive water management program should first and foremost improve human health and safety by achieving alignment with regulations and standards. It improves water and energy efficiency by achieving sustainability targets. It optimizes the lifespan of capital assets, such as boilers, chillers, and cooling towers. It optimizes the costs associated with buying, heating, cooling, and treating the water. And lastly, it documents all of these activities for defensibility purposes. Remember, you cannot manage just safety or efficiency as one impacts the other. Next slide. Now, let's turn to improving efficiency and reducing costs. An efficiency water management program should focus on operational changes that result in immediate cost savings without jeopardizing performance, your capital assets, or water safety. We're not talking about large capital expenditures that have 10 to 20-year return on investment timeframes. In most facilities, the biggest opportunities lie in the utility water systems. But that is no longer always the case as building owners dedicate more and more resources to operating their potable water systems safely. An independent evaluation of your expenditures in both areas can turn up significant opportunities to conserve resources. So here are some specifics. Our focus on the rest of the presentation will be on chiller efficiency. But here's a general overview of the utility water savings opportunities that we have seen in various facilities around the country. The biggest portion of most large facility budgets goes towards the heating, cooling, treating, purchase, and disposal of water. It only makes sense that there would be significant opportunities to save costs in these areas. These savings opportunities are not always present in many facilities, but there are very few facilities where we find zero savings. And in some cases, the savings discovered as a result of developing and operating a comprehensive water management program pay for the entire safety and efficiency program with dollars left over. Okay, the preceding slides were the 100,000-foot overview. We're now going to dive into some of the issues that impact chiller efficiency. This is not a physics course, so don't tune out just yet, but it is important to understand on a very basic level the physics of your HVAC system. Chiller energy is a function of load and lift. Load refers to the cooling demand on the chiller. Lift refers to the difference in pressure between the refrigerant in the condenser and the refrigerant in the evaporator. The greater the pressure difference, the more work that the compressor is having to do or energy that needs to be added to the process in order to meet the demand for a given load. We will come back to this relationship, but we will leave the physics out of the next few slides. Why is chiller efficiency important? Well, did you know that centrifugal water chillers can account for 20 to 40% of a facility's total energy consumption? Or that it can lose 30% efficiency and appear to be operating satisfactorily? This is an example of a typical chiller plant in a large building or small college campus complex. The assumptions are that the plant is running at an efficiency of 65 kilowatts per ton. The cost of electricity is 6 cents per kilowatt, and that the equivalent full load cooling hours is 3,000. EFLH is the number of hours a chiller system would have to operate at full load to equal the amount of cooling delivered by the system at a constant temperature over an entire cooling season. Of everything we have discussed so far in this presentation, if $175,000 in lost energy does not get your attention, then it's time to stop looking at the emails or texting and pay attention a little bit more. So, even with brand new chillers that collect reams of continuous data that is recorded somewhere in your building automation system or the chiller itself, we still find facilities maintenance personnel recording some of it on a clipboard. In addition, every chiller has alerts or alarms to warn of serious problems, and everyone performs periodic maintenance. But in the majority of facilities we see, there is no analysis of the data collected that shows you where you are on the continuum between operating your chillers at design efficiency or operating your chillers at the ragged edge of efficiency or even failure. So with that, let me turn it over to Larry for the next couple of slides.
Okay, thanks, Mike. Appreciate that. Mike talked about collecting data on a clipboard and log sheet, and I've been in the business for over 50 years, and there's still a lot of folks today that do the same way they did when I started 50 years ago, and that's the clipboard and log sheet, and it can be useful. It can be functional if you do it the right way. But here's an example of an 800-ton chiller in a hospital. They had 2 of these 800-ton crane machines in the hospital. And if you look at the log sheet, they're logging it about every 4 or 5 days. The good news is they're getting a lot of data into the log sheet. They're getting the temperatures down to 1/10 of a degree, which you don't see that often, getting that close on temperatures. So they've got an awful lot of data here, okay? But what they don't have is analysis. So Mike, take it to the next slide, please. And if you look closely at this log sheet, you'll see that down in the condenser section, they're running approaches of 10 or 11 degree approaches on the condenser, if not higher, on a chiller that should have about a 1 or 2 degree approach at full load. And what that indicates is about a 20% efficiency loss. And for the way this chiller operates and their load analysis, it's probably costing them in the order of $18,000 to $20,000 per year per chiller for a problem that, number one, is easily identifiable if you look at the log sheet properly and do the right calculations. So the point I'm trying to make here is that collecting data by itself doesn't get the job done. You have to have a process for analyzing the data to get the results that you need. Next slide, please. This is a slide from a chiller plant in a large facility that had a total of about 40,000 tons. This is a log sheet for a 1,500-ton chiller. And again, if you look at the log sheet, you can see that it's logged every week or so, every 5, 7, or 8 days. They've got a fair amount of data. They don't have it down to a 1/10 of a degree, but they got round numbers in there. And if you look under the temperature columns, under the condenser liquid column, the data is mostly blank. You get down where that red arrow is, and they finally entered a number for the saturated refrigerant temp in the condenser. You then back up and look at the temperature of the water leaving the condenser at 84. That's about a 9-degree approach. That's about a 16% efficiency hit on this machine, 1,500 ton machine. And that alone is about a $47,000 per year waste in energy. So they had a fair amount of data. They got complete data later in the program, but they didn't do the analysis necessary to tell them that they had a very significant issue. And the interesting thing about this log sheet with this customer, I found out actually later, was the log was not taken by the owners themselves and their operations people. This log was taken by their service contractor, who had a contractor come in periodically, review the chiller operation, and tell them how well it's running. So the point here that we learned back then was that the owner really has to take responsibility for getting the right data, getting the right analysis, and making sure that your chillers and your chiller plants are running efficiently. Back to you, Mike.
Thanks, Larry. So this is a laundry list of some common and some not so common chiller problems that can cause efficiency losses. You may have one of these, or you could have multiple issues at the same time. The key is that you all have or can easily get the data you need to uncover these problems, although you do have to do some algebra and analysis to get there. If necessary, you may need to ask your teenager for some help on the formulas. So, condenser approach, you heard Larry talking about it. One of the most common problems we see, and one of the easiest to identify, is condenser approach. Condenser approach is the difference between the temperature of the water leaving the condenser and going to the cooling tower, or T1, and the temperature of the liquid refrigerant leaving the condenser going to the evaporator, or T2. The refrigerant is being cooled and changes from a gas to a liquid in the process. The water absorbs that heat in the condenser and carries it to the cooling tower, where it is released into the air. If everything is working the way it should be working, the difference between the two temperatures should be less than 2 degrees at full load. This means the heat is being transferred efficiently. So let's get Larry to explain in a little bit more detail for us what's going on.
Okay, let's take a look at it. It's a single condenser tube. We got water coming from the cooling tower at 85 degrees, going through the tubes, exiting at 95 degrees. So it's a 10-degree load. This is probably full load for this machine. Gas is coming in off the compressor in the range of 130, 140 degrees. It then condenses from a gas to a liquid, gives up its heat to the water through the copper tubes, and that heat is rejected out to the cooling tower. So in this case, we're dripping off the tubes at 96 degrees. That's our 1-degree approach that we're looking for. Ideal conditions, full load, clean tubes, 1-degree approach. Keep in mind too that if we were running at a 50% load, we would expect the approach to be half of what you see at 100% load. So the 50% load, a 1/2-degree approach would not be unusual. It would be expected. Next slide, Mike. Now we take a situation where we've got a buildup in the tubes. And again, as Mike indicated, the number one issue we see in chillers all over the country, the number one problem, most common problem, is high condenser approach, or tube fouling. And there's good reasons for that, because of your open air wash system cooling tower. But with these systems, there's a lot of opportunity for fouling. It can come from scale, bacteria, sediment, microbiological fouling. We're seeing a lot more microbiological fouling than we used to see many years ago, and we had different treatment processes. And as that fouling builds up in the tube, the refrigerant temperatures have to go higher in order to force that heat out through the tube, through the scale, into the water. That raises the refrigerant pressure. As the pressure goes up, energy goes up, efficiency goes down, cost goes up. So you want to make sure that you're keeping those tubes as clean as you can. identifying if there's fouling, correcting it in a timely manner so that you don't waste a lot of energy. Next slide. Now, over the last 20 or 25 years, a lot of manufacturers, or all the manufacturers, have improved chiller efficiencies by going to what they call internally enhanced tubes. What they do is on the interior of the tube, and it used to be smooth bore throughout. Now, with this enhancement, it turbulates the water. You get much more turbulence in the water. You get much better heat transfer effect between the tube and the water. Okay, but it also provides an opportunity for fouling. The tubes you're looking at on the left side, in the very top, is it's a cutout view of a clean tube. Below that is an internally enhanced tube that's got microbiological fouling. If you look at the slide on the right, this is a reading that we took to get an idea what was in the tubes, and you can see the grooves in the tube. You can see the microbiological scale, slime. This resulted in a very significant energy efficiency loss on that chiller. And one thing that you need to understand is with internally enhanced tubes, how they're cleaned is important. The right process, the right method. You have to use the right kind of brush, two-direction brushing, and I think Mike is going to go through that in a little bit more detail. But there's a right process and a wrong process to clean these tubes. Make sure that whether you're cleaning them or your contractor's cleaning them, that they're following the right process for cleaning internally enhanced tubes. And you can identify these problems, obviously, with a good logging process. A good logging method will tell you if, in fact, you've got significant fouling. Okay, next, Mike, back to you.
Thanks, Larry. So based on what we have learned in the previous slides, you're probably saying, okay, so what do I do? Well, this is our recommended approach or process. I'm going to read this whole slide because it's going to be on the test at the end of the presentation. You know, and although I'm kidding, of course, about the test, this is the sort of the how you do it slide. So it's important. Capture necessary data and input it into a database or a spreadsheet, but you got to record it. Manipulate the data and calculate the approach temperatures, efficiencies, and other things. That's where your teenager and the algebra comes in. Then you need to analyze the data and identify the problems. Then you take each problem, verify that there is a problem, because it's not always the case that there is, and then determine the cause. Then determine if fixing the problem is worth the time and expense. Is there a return on your investment of maintenance dollars? Do you really need to open the chiller up? You then implement the corrective action. Then you need to make sure that the corrective action actually worked. And then you go through and fix every problem on every chiller. And then you start all over again and monitor for new problems on a continuous basis. Sounds easy, right? We'll go through some of the steps in more detail in the next few slides. So, first, you need to collect the necessary data. You don't need thousands of data points. In fact, you can get by with just one set of readings a day at or near peak load. And you can even do it manually, but you do need a place to store the data. Next, you need to perform some calculations and then analyze the results. This will enable you to begin to identify where you may have problems, such as this picture of a tube bundle opened up. And no, you should not use your tube bundle as a filter as shown in the picture. So, you've identified some problems that are as a result of your analysis of the data. It would be too easy if that analysis directly pointed to one specific problem. Unfortunately, that is not the case. It's a process of elimination. If you are lucky, it may be just a gauge out of calibration. Sometimes it is not an easy or inexpensive fix. Other issues may be hard to confirm or expensive to repair. When you get to one of those problems, you need an idea of what the potential return on investment is. Said another way, is the cost of the repair or maintenance going to be more than the energy dollars you are going to save? If that's the case, you may choose to defer the repairs until a later date if the ROI is not significant. Perhaps when you can combine several repairs into one. That doesn't sound like the greatest solution from a maintenance mechanics perspective, but from an efficient use of maintenance management dollars, it may make sense. The next step is to implement the solution to the problem. In this case, the indicated solution was to open the condenser and brush the tubes. This is not an inexpensive task, but as you can see, the potential ROI was over $30,000. The approach before the brushing was 13.7 degrees, and the approach after brushing was 7.2 degrees. A marked improvement, but the desired result was less than 2 degrees. So what went wrong? This type of work is often done by an outside vendor. So with proper data analysis, you can now verify if the vendor did what they said they were going to do. After further investigation, it was discovered that the vendor had only brushed the tubes in one direction, and thus the work did not achieve the targeted ROI. This is what Larry was referring to previously. You've got to do it with the right tools in the right way. So after the initial brushing, the new data showed that there was still a potential ROI of over $19,000. The vendor was required to come back and brush the tubes in both directions. The new approach after brushing was 0.5 degrees. The efficiency of the chiller was restored, and you are now able to show, with data, the value of performing the maintenance or repair. Larry, with that, let me turn this one back over to you. Larry, are you there, or did you mute? Monica, can you hear?
Hey, Mike, I'm here, but I cannot hear Larry either.
Okay. Well, change the program. I will pick it up.
Great.
All right. Performing maintenance tasks only when needed is not something new. But generally speaking, it is not always easy or inexpensive to implement. But with the same data we have been collecting to monitor and correct efficiency problems, you can implement a condition-based maintenance program on your chillers. Why are you?
Let me step back in.
All right.
I'm sorry.
You got it?
Go ahead. Let me back in. I got it. Appreciate that. Yeah, this is a real close issue for me because we learned a lot about this when we started this a number of years ago at a big university. But most cases today, maintenance tasking is done on a fixed schedule. If I were to ask everybody how often you brush condenser tubes, you'd probably say we brush them once a year. We do them during the annual maintenance, those types of things. If I were to ask when is the right time to brush tubes, the answer should be they should be brushed when they're dirty and not brushed if they're clean. If you can maintain good water treatment conditions, keep your tubes clean through the normal water treatment process, and maintain the approaches the way they should be, then you really don't need to brush them every year. Okay, next slide. This is an example of a university that had about 38 chillers. They had a lot of issues to begin with, a lot of water treatment issues, maintenance issues. We went through a whole series of processes to get everything running in the right direction and get them back online. And what we found out was after we implemented the processes, we used the program of logging and log analysis to determine if in fact there were issues that we needed to look at from a maintenance standpoint. The change in their maintenance procedures over the years, in year one, they were brushing every chiller 2 men, 2 days per chiller to drop heads and brush tubes. After the first year, using the new water program implementation, the new logging process, they only had to brush 15 of the 38 chillers. And then from there, it dropped down 8 chillers in year 3, 2 chillers in year 9. So the savings just in manpower was big. The savings in energy was huge. So using condition-based maintenance, you can use it for leak testing, let's say. If your chillers, evaporator approaches are as good this year as they were last year, and your purge pump out frequency is low, you don't need to shut that chiller down and leak test it. It's an expensive process. You can leak test based on evaporator approach rates. Oil analysis, we don't use logs for oil analysis, but you can do the same approach with oil analysis to determine if you need to do an oil change every year. So we think that looking at data analysis is a big factor in determining maintenance schedules can really save you a lot of time, a lot of money, and a lot of effort. Back to you, Mike.
Okay, thank you, Larry. So I promised about 30 minutes, and I think we're about there. So we'll have plenty of time for questions. To wrap this up, chillers are expensive to operate, and small losses in efficiency add up fast. If you're going to take action, you must record chiller data at least weekly and preferably daily, if not continuously. You must analyze the data regularly, identify problems, determine solutions, and calculate the ROIs in order to make informed maintenance decisions. Then, of course, you must take action and implement the maintenance or repair actions with an ROI and restore efficiency. Lastly, you must always validate or measure if the efficiency was actually restored. So I always like to end with a question. You have many options for automating data collection, analyzing the data, and then making informed decisions on that data in order to maintain or restore chiller efficiency. But do you know the operating efficiency of your chillers at your facility? So, did we achieve our learning objectives? Let's see. I think we described how a comprehensive water management program can be used to capture the efficiency gains in a building water system. And we showed you how chiller efficiency fits in amongst the other aspects of utility water efficiency. Then we identified the challenges that arise in maintaining chiller efficiency, including the short and long-term financial impact of not addressing them in a timely manner. And although maybe not simple, we demonstrated how to easily monitor, trend, and identify challenges by analyzing readily available data that you are probably already capturing. Lastly, we discussed manual and automated methods for analyzing the data, calculating ROIs, and easily managing your chiller efficiency using a minimal amount of time and resources. I think we covered all these pretty topics thoroughly, and let's see how well we did with the number of questions we get here. So, thank you for your time and attention today. We have a lot more information, videos, white papers, and other presentations, etc. on our website. Or if you would like to ask specific questions after the webinar, please shoot us an email or give us a call. So thanks to everyone, and back to you, Monica.
Great, thank you, Mike and Larry. We have gotten several questions in, so we'll get right into them. The first question that I have for you, and Mike, you can decide to answer it or pass it on to Larry, is how do I know when it's time to take down and clean my chiller tubes?
Okay, Larry, you want to take that one?
Yeah. What you do with the program that Mike and I were talking about, you enter operating data, you look at your condenser approaches, you calculate what we call your excess approach, and then you apply that approach to a efficiency loss formula. And you typically are going to lose about up to 2% efficiency for every 1 degree your approach is higher than it should be. So if you have a 10-degree excess approach, you could be losing 20% efficiency. And what some of the programs do, you take that percent loss and you apply it to a run hour calculation that predicts how many run hours and what percent load your chiller typically runs per year. And you say, if we ran that whole year with that efficiency loss, what would it cost us in energy? And that gives you the ROI that Mike was talking about. You can say if the savings is $12,000 and it will cost you $1,000 for brushing, that's a pretty easy ROI to calculate. So on the condenser side, if the approaches lead you to believe that you're going to waste energy in an amount greater than it would cost you to fix them, you have to make that decision. Should we shut it down and fix it? The other thing you want to do at the same time is determine, why are my approaches going up? You want to call in your water treatment company and say, our approaches are going up. There's something changing in the water treatment process. We need to stop the approaches from getting higher. So there's two factors involved: to stop the progression of the problem and determine whether you need to brush the tubes or not.
Okay, great, got it. Thank you, Larry. The next question that came in is, how do we need to change or address the building automation system so that it can use the data we already have for this water improvement program?
I'll try to answer that. Well, not all building automation systems are, meet the same standards, have the same functionality. Obviously, that's why they, there's multiple opportunities, or there's multiple systems out there. There are systems that will take the data from the building automation systems and run these calculations for you. I mean, that's what we do. We have our own. There are other options out there, but we like to think ours is better than anything you can find in a building automation system. I just know, having been a former facility professional and director of facilities at the Naval Academy, dealing with a couple of the large companies, getting them to do anything to change their building automation systems is, sometimes a long, arduous, and very expensive process. So look for the little plugin that can maybe get you where you need to go without having to deal with the building automation system at all, I guess, is the short answer to the question.
Okay, great, thank you. The next question has to do with a different type of chiller. So with respect to the approach temperature / efficiency loss connection that was discussed, is that the same in a scroll chiller?
Yeah, it's the same in a scroll or screw or water-cooled centrifugal. What we're talking here primarily is water-cooled centrifugal scroll and screw. And typically, when you get these chillers new, you get from the manufacturer's data sheet, design data sheet, and typically it's going to give you design approach temperatures or condensing temperatures, numbers that you can relate back to what should those approach temperatures be at a full load condition. And in all cases, you want to get all the manufacturer's data you can, including those target approach temperatures, so that you can program your process to look very specifically at what your chiller should be doing.
Okay, great. Thank you, Larry. The next question is with respect to non-chemical water treatment. So the question is, are there non-chemical water treatment options that meet the code requirements? And if so, what are they?
I'll take a shot at that. Are there non-chemical water treatment devices out there? The answer is yes. I guess the subtle way to respond to that is, we've never seen any of them that work on a consistent basis, I guess. And so we, who have a view of the entire marketplace of different ways to manage the treatment of your water, we've never found a non-chemical device that we would recommend. And
Okay.
I'll leave it at that. I'm not sure if that completely answered the question, but if it didn't, please shoot me one and we'll get into more detail.
Okay, great. So there's a couple questions around acid cleaning versus brushing. So I'm going to try to formulate this in what I think the question is. So if you increase the duration between cleaning, the amount of time in between cleaning, does that cause the cleaning process to have to use acid cleaning versus being able to brush the tubes? So so how I'm interpreting this question is, if you have a shorter duration between cleanings, can you be able to brush the tubes? And if you wait longer, are you setting yourself up for acid cleaning versus being able to brush tubes?
Mike, you want me to take that one?
Yep, you got it.
Yeah, there's really no connection between the laying brushing, because the approaches are good and a buildup of calcium carbonate scale that would need to be acid cleaned. They're two totally different concepts. I've seen customers go 4, 5, and 6 years. Typically, they might want to do an eddy current test every 3. So if you do that, you're going to take the heads down, you're going to brush them anyway. But there's really no connection I don't see between not brushing every year and a buildup of scale that would require acid cleaning.
Okay, great.
Right.
Okay, so another somewhat technical question. What should the approach be on the evaporator side?
That varies a lot by manufacturer, by age, and by tonnage, and by size. And what it should be on the evaporator side, it could be anywhere from 2 to 6, 7, or 8 degrees, depending upon the age. Now, what I recommend here, again, like I mentioned before, if you're going to be setting up a really well-maintained logging process, you need to go back to the manufacturer with the model number and serial number. So get me the design data for these chillers. I want to know what the design saturation temperatures are for the condenser and the evaporator, so that you'll know exactly what the design, and even if that chiller is 20 years old, you should still be able to achieve those approach temperatures. So start with the manufacturer. If you don't, we have numbers that we use to estimate what those approaches could be based on age. But typically you want to get as close as you can from the manufacturer. But in the evaporators, they can be significantly higher than in the condensers.
Okay, great. The next question is around chiller surge. So what are the top ways or options to eliminate chiller surge?
Well, that's a good one. Surge occurs for a couple of reasons. One is a heavy load surge, where your condenser pressure is higher than the lift capability of the compressor, because probably due to foul tubes or air in the machine or low condenser water flow or high condenser water temperature. Your head pressure is getting too high, your evaporator pressure is getting too low, so that you have a reverse flow of gas through the compressor. The way to handle it, obviously, is find out why my head pressure is so high. Is it a water temperature, water flow, foul tubes? What is causing that to be higher than it should be? Light load surge occurs under very light load conditions, and I'm not really sure with the new chillers today what process you would take. I haven't heard much of that lately, to be honest with you. So I don't really have a good recommendation on the light load side, other than to talk to the manufacturer, say, these are the conditions my chiller is running at, give them a full set of log readings, say, tell me why my chiller is surging under these conditions, and what should I do to correct it.
Okay, great. So this next question, again, is a pretty technical question. I'm going to do my best. So in low pressure centrifugal chillers, what is the trigger point of concern if the purge pump out increases steadily each 24-hour cycle? Does that question make sense to you?
I'll be happy to take that one.
Great.
You want to take it, Mike? Okay.
You got it.
Well, okay, wait. Before you get into that one, there's a second part to that question, and I'm not sure if these are related or not. So I'm going to go ahead and read it, but maybe you want to take them separately. So the first part is the trigger point of concern, and then the second part is what saturated suction temperature reading would I expect if my pump out seems to be getting excessive. So I'm not sure if those are two separate questions or if they're related, or if you could cover those together.
No, they're related. Low pressure refrigerant, I'm talking either about an R11 or an R123 chiller. And they operate under, the evaporator operates under a vacuum during normal operation. The condenser operates under positive pressure, and each of them has a purge on it that should you develop a leak in the evaporator, wherein air leaks into the machine while it's running, that air then gets ejected up into the condenser. The purge has a process that continues to recycle and remove that air out of the machine. Now, the new purges today, well, going back a number of years, have a nice feature that they keep track of the number of minutes that they've actually purged air out of the machine. So there's a relationship between the purge minutes per day and the amount of air they've taken out, which is a relationship to the size of the leak. A lot of manufacturers will have a number of minutes per day. You don't want it to purge more than 15 minutes a day or 30 minutes a day. You want to look at what the manufacturer recommends for your machine. But if you go over the recommended purge time, it's telling you that you have a leak in the machine. If you have a leak in the machine, you're drawing air in the machine, you're drawing moisture into the machine, the air is getting into the condenser, raising the head pressure, it's costing you energy. So you want to, at some point, shut the machine down, have your contractor shut it down, leak test it, identify the leak, and fix the leak. Now, regarding the saturation temperature in the evaporator, if you're losing refrigerant due to a leak, and your evaporator approaches are starting to go down. That's what happens as you lose refrigerant, the refrigerant level drops in the evaporator, the approaches will start to go up. Your saturation temperatures are going to follow the pressure down because of the loss of refrigerant. So you want to monitor that. That's another big indicator with your logs. It's tracking your evaporator. We talked about condenser approach all that. The evaporator approach is the same thing. Only in the evaporator, it may be due to foul tubes or it may be due to a loss of refrigerant. So you want to monitor evaporator approaches just as carefully as the condenser approaches and identify, do I have a leak in the machine? Is it big enough I need to fix it? What's happening? Okay, back to you.
Okay, great. So we just dug really deep into some technical content there, so that was great. I have one more question left. And so we'll cover that and then we'll wrap up. So the last question is, and again, I want to thank you all for submitting these questions. These have been really good questions. The final question is, when we talk about brushing the tubes, what does it mean when you say brush in two directions or brushing tubes in two directions?
Oh, I want to take that one, Mike, please.
Yep, you got it.
We learned this, the slides that Mike showed was the process where we really learned the right way and the wrong way to brush tubes. This goes back a number of years. And with internally enhanced tubes, it takes a different kind of a brush. It takes a brush that turns in both directions. That's clockwise and counterclockwise. Okay, so my recommendation to any owner who's got chillers is if you have a high approach situation, and you want to drop the heads, inspect and brush the tubes, first thing you do is call your water treatment guy, have him come out with a borescope. Okay. The reason being, when those heads come down, you want to find out what is causing the high approach. Is it microbiological? Is it dirt? Is it calcium carbonate scale? What's going to be the right process to clean those tubes? And in many cases, you have to look down into the tubes with a borescope to identify, okay, what's in the tubes? What do we need to clean? I've seen customers on 2,000-ton machines have the contractor come in, brush the whole bundle, and not make one change because of the scale in the tubes. If you'd have looked, you'd have seen it right away. You would have asked. So you want to identify what's in the tubes, and then if it is a brushable, if it's microbiological, slime, dirt, that type of a deposit that's brushable, you want to use a machine that turns the brush in both directions, okay, clockwise and counterclockwise. You want to use the right brush. Don't use the old blue nylon brush. That's for smooth bore tubes. Internal enhanced tubes use either a red, white, and blue, what they call a Patriot brush, or a grit impregnated nylon brush. It's got to be the right brush. So you have your water treatment right there with the scope, you start brushing. The next question is, well, how often should I change the brush? Anybody know the answer to that? The answer there is you change the brush when the brush stops getting the tubes clean. Well, how do you know when that happens? If you're looking at the guy brushing the tubes, every time that brush goes down and back, it wears that brush out a little bit. So the brush becomes less and less effective. So you've got to have a way to look, okay, when did the brush stop getting the tubes clean? And again, if you have a borescope, What I recommend is, okay, brush the whole top row, borescope the last tube, you brush. If it's clean, do the second row. Check the last tube. If it's clean, do the third row. Go until you find out when that brush stopped. It may be after 10 tubes. It may be after 2 rows. We don't know. So you have to take a look. You have to determine the right brush, the right two-direction brushing, and determine how often or when to change the brush. Back.
Okay, great. So we did get a couple more questions in, so I'm going to cover one more at least right now. And let's see, how does using the Hartman loop on the chiller plant impact the energy savings and water treatment?
Boy. Mike, you know the answer to that?
Nope, we'll put that down in the, we'll get back to your questions.
Okay. Okay, I wasn't sure. But then...
Good question.
Okay, great. So then again, the final question that I'll pose to Mike, you and Larry is a question about the software itself. And is there a spreadsheet available for download with this analysis built in?
No, this is not a spreadsheet-based program that we use. It's an online database application that you put your data in and it spits out the information for you, as well as the ROI, the places to look, the possible problems you may have, the possible solutions. It's a one-stop shop. It's Larry in a box, almost.
Fantastic, almost, right? Okay, great. And again, thank you all for submitting these questions. This has been a great list of questions, so we appreciate that. And Billy, I'm going to turn it back over to you to close us out.
Okay, well, thank you so much. Larry, Mike, Monica, thank you so much for your time for today's webinar. And for our attendees, thank you so much for taking time to be with us today. So until next time, be safe, stay healthy, and have a great weekend. Bye now.